When stability turned into chemical inertia, it felt like success. Everything worked, nothing changed, and that was the problem. The absence of change was celebrated as proof that the system had been perfected, when in reality, it was the first sign that the system had stopped evolving. Stability is often treated as a victory in chemistry. Reactions that behave consistently are celebrated. Systems that resist change are trusted. But stability has a hidden edge. When chemistry stops changing, it can also stop adapting. The same qualities that make a reaction dependable under known conditions make it vulnerable when those conditions shift. Stability without adaptability is not strength. It is rigidity waiting for the right pressure to expose it. To understand why this matters today, we need to look at how stability becomes inertia. A reaction that performs reliably earns confidence. Confidence reduces oversight. Over time, systems stop asking whether stability is still serving its purpose. The question fades because the answer has always been the same, and no one notices the moment when the answer quietly changes while the question is no longer being asked. At first, the chemistry delivered exactly what was needed: predictable outcomes, minimal variation, processes that could run uninterrupted for years. Stability felt like mastery. It was the kind of performance that justified itself with every cycle, offering no reason for reconsideration and no incentive to explore alternatives. As reliance deepened, change became inconvenient. Adjustments introduced risk. Experiments felt unnecessary. The chemistry worked, so it was left alone. Stability hardened into routine. The distinction between the two dissolved without ceremony. What had once been an active achievement, maintaining a reaction within precise parameters, became a passive inheritance, something the system did not because it chose to, but because it no longer remembered how to do anything else. What made this dangerous was subtlety. Nothing failed, nothing broke, but conditions around the reaction shifted slowly. Inputs changed, pressures increased, chemistry stayed the same while the world evolved. The divergence between the static reaction and its dynamic environment grew at a pace too slow to trigger alarm, but too steady to remain harmless indefinitely. This is where the story begins. With a system so stable, it stopped responding. A chemical success that quietly turned into inertia long before anyone realized stability had become a liability. As the chemistry remained unchanged, everything else began to move around it. Demand increased, environments shifted, new stresses appeared, but the reaction stayed locked in its original form. It operated as though the conditions of its design were permanent, while the world around it demonstrated with increasing clarity that nothing is permanent. At first, this rigidity seemed harmless. Stability absorbed early pressure. Minor variations were smoothed out. Chemistry continued delivering the same results, reinforcing trust in its permanence. Each successful cycle under changing conditions appeared to validate the decision to leave things as they were, even though each cycle also consumed a slightly larger share of the margins that made stability possible. This is where early tension emerged. The system could handle small changes, but only by working harder. Energy input increased. Maintenance intensified. Corrections became constant. Stability was no longer effortless. What had once been a natural resting state of the reaction now required sustained force to maintain. The effort was invisible in the outputs, but mounting steadily in the inputs. And no one tracked the growing cost because the results still looked the same. Scientists noticed a subtle pattern. The reaction was no longer adapting. It was being propped up. Chemistry that once balanced itself now required continuous intervention to remain stable. The equilibrium was no longer intrinsic. It was engineered, maintained not by the reaction's own properties, but by the constant application of external force to prevent it from drifting toward a new and unfamiliar state. This created a dangerous feedback loop. The more effort invested in preserving stability, the less willing systems were to accept change. Alternatives felt risky. Adjustment felt disruptive. Inertia strengthened with every cycle. The investment in maintaining the current state became its own justification for continuing to maintain it, regardless of whether that state still served the broader purpose it had been designed for. What made this difficult to detect was success. Outputs remained consistent. Failures were avoided. Chemistry appeared reliable, even as flexibility vanished beneath the surface. The metrics that everyone watched continued to look healthy, while the capacity to respond to disruption, a quality no metric tracked, eroded steadily. and silently. Stability had stopped being a feature of the system. It had become a constraint, and chemistry, once responsive, was now resisting the very changes it was meant to support. The system had crossed an invisible line where the effort to remain stable exceeded the benefit that stability provided, but no one could see that line because no one had thought to define it. The conflict intensified when pressure finally exceeded what inertia could absorb. Small disruptions that once passed unnoticed now caused outsized effects. The system no longer bent, it resisted. The rigidity that had masqueraded as reliability revealed itself as brittleness the moment conditions demanded flexibility. Chemistry revealed its limit. Stability maintained through constant correction is not resilience, it is delay. The reaction still functioned, but only within an ever-narrowing window. Outside that window, failure was sudden and severe. There was no gradient between working and not working. The system either held or it broke, and the space in which it could hold was shrinking with every cycle. This buildup carried emotional weight because the warning signs had been visible for years: rising energy costs, increasing maintenance, growing sensitivity to variation. Each was treated as an operational issue, never as a chemical one. The symptoms were managed individually, never connected into the larger pattern they collectively revealed: that the reaction was no longer naturally stable, and that the system was spending more and more of its capacity simply preventing collapse. Attempts to force continued stability made matters worse. Tighter controls reduced tolerance. Faster responses increased brittleness. Chemistry was being held in place instead of allowed to evolve. Every intervention designed to preserve the status quo made the status quo more fragile, creating a cycle where the solution to instability produced deeper instability. This was the emotional peak. The realization that the system was no longer stable at all, it was frozen, unable to adapt, unable to recover. Chemistry had been optimized into immobility. The appearance of stability was being maintained at a cost that had become unsustainable, and the moment that cost could no longer be paid, the entire structure would fail at once. What once felt like control now felt like fragility. The reaction was no longer supporting the system. The system existed only to support the reaction. The relationship had inverted completely, and the inversion had happened so gradually that no one noticed until it was already irreversible by incremental means. Stability had crossed a line. It had become chemical inertia, and inertia does not negotiate when conditions finally demand change. The climax arrives with a hard truth: stability that cannot change is not stability at all. Chemistry did not fail when inertia took hold. It followed the conditions it was given. The failure came from mistaking constancy for health. Systems were rewarded for staying the same, even as the world demanded adaptation. The metrics measured consistency, and consistency is what they got. But consistency in a changing world is not the same as fitness, and no one had built a metric for fitness. This realization reframes resilience. True stability is dynamic. It allows movement. It absorbs stress by changing shape, not by resisting it. Chemistry thrives when it is allowed to evolve with conditions. A reaction that can shift its equilibrium in response to pressure is far more durable than one that must be held rigidly in place. The resolution lies in reintroducing motion, allowing reactions to adjust, accepting temporary disruption in exchange for long-term adaptability. Stability becomes a process, not a state. It is something that must be actively maintained through responsiveness, not passively assumed through repetition. This story is not about abandoning reliable chemistry. It is about refusing to fossilize it. Reactions chosen once should not be preserved forever without question. The willingness to revisit, to adjust, and to accept the discomfort of change is what separates systems that endure from systems that shatter. When stability turns into inertia, chemistry becomes a liability. When flexibility returns, chemistry regains its power to support progress rather than constrain it. Understanding this difference may be the key to designing systems that survive change instead of collapsing under it. Subscribe to join the journey. When